What does the calendar say we're going to do the rest of the week? Have fun. Very nice. What sections? Okay, we're going to cover 4.3 and 4.4. Now we're actually going to cover both of those together. It might take 2.5 or 3 days to get through the explanation for both of those sections. They are very closely related. By the time we're done with today's explanation, you'll be able to do most of 4.3 and some of 4.4, okay? And then over the next couple days, we're just going to fine-tune this. We've gone from graphing very simple functions like parabolas, quadratic functions and that sort of thing, to graphing these weird-looking polynomials with all these wiggles and turning points and all that sort of stuff, knowing whether it touches or crosses at an X-intercept, being able to look at a graph and saying, oh, this is the power function that could have produced this or something like that. We're now going to add to the things that we're able to graph, okay? And we're going to graph rational functions today, all right? So let's take a quick look here. And just a reminder of a couple terms. Is that proper or improper? Okay, that is proper. Now, it's proper, but is it reduced? It's not reduced, okay? So we could just reduce this to 1/2. Either way, those are both proper fractions, okay? If I take a look at this right here, is that proper or improper? Okay, so this one is improper, okay? This one is proper. And how about this one right here? Is that proper or improper? Okay, the way it's written, it is improper. Okay, now it's not simplified. We could simplify this. Okay, would everybody agree that this type of improper is better than this type of improper? Yeah, because this one, if you made this into a mixed number, this would be like 2 1/6. Okay, this one is really easy to simplify. Both the top and bottom are the same, so we could just write that as a 1. So as a fraction, it's improper, but we could easily simplify it. This is kind of an ugly type of improper, and regular old proper fractions, they're nice. The best that we could do is just simplify them, okay, reduce it, okay? State the degree of each polynomial. Now, don't say this out loud. We went over this the last couple days. We should be able to look at that and just state what degree the entire polynomial is. I'm asking that question in a little bit of a misleading way. What's the degree here, Alex? It's degree 3, okay? Because it's just the highest one, right? We don't really care about these other guys right here. It's just the highest exponent, okay? We don't add them together or anything. Okay, Chase, what's the degree of this polynomial? This would be degree 1, okay? And Sam, how about this one right here? What degree would the 7 be?
0.
It would be degree 0, okay? Because remember, you could always slap an x on there and put it to the 0 power. That would make it just a 1. 7 times 1 would be 7, okay? All right, so this section is about graphing rational functions. These are going to be pretty wild. These will probably be the weirdest graphs you've ever done. But let's start off by talking about what the root word for the word rational is. Anybody know what it is? Yeah, ratio, just ratio. Okay, and ratio is a fancy name for what? A fraction. So when we say we're going to deal with rationals, we're going to be dealing with fractions. Now, these are rational functions. So these are functions that have fractions in them. Doesn't that sound thrilling? That's what I was thinking, okay? Now, in order to get these right, there's a lot of logic that we're going to use, a lot of the tools that we learned with factoring and polynomials and all that sort of stuff that we're going to figure out. But it's going to take a lot of skills. We're going to be factoring, we're going to be simplifying, we're going to be doing some division and all sorts of stuff. But there's really no substitute for just sitting down and thinking about, okay, how are all of these pieces that I know about this rational function, how are they related? How can I figure this out, what this looks like? Okay, now that's the cool thing. Right now, some of these are going to look overwhelming and weird and like, my gosh, how am I ever going to figure this out? By the end of the week, in fact, I would say maybe by the end of today, you'll be able to figure out how to graph something that looks really awful, okay, but do it pretty quickly and understand for the most part how it works. By Friday, you're going to be a pro at it, okay? So the first thing we're going to do is we're going to define what a rational function is. A rational function looks like this. So we'll use r of x, r for rational. It's p of x over q of x. Now, p is a polynomial and q is a polynomial, okay? P and q are polynomials. And q is not the 0 polynomial. The denominator can't be 0. Remember, we've got a fraction here, we've got division. Division always introduces a domain issue. You can't divide by 0. And that's really what's going to make these graphs look kind of cool. Okay? So as long as you've got a polynomial divided by a polynomial, you've got a rational function. Okay? The domain of the rational function is the set of all real numbers, because remember, if these two are polynomials, you can plug anything you want into a polynomial except what makes q equal to 0. Okay? Those are the numbers that we're going to have to throw out. Okay? And we've actually seen some problems like this before. Okay? And the reason we can't have q equal to 0 is because we've got that division in there. Okay? So we're going to look at some really simple rational functions to start off with. All right. So let's take a look at this one right here. This is the reciprocal function, right? Well, we've already graphed this. We graphed this a couple weeks ago, or last week. What does the rational function look, or excuse me, the reciprocal function look like? Yeah, it's got this branch over here and this branch over here. So it's got a piece that looks like this, like that, and a branch that looks like this. And then we've got this vertical asymptote right here. So the vertical asymptote is x equals 0. And we've got this horizontal asymptote, y equals 0. And remember, we went over this. The reason this gets really big, by the way, it does go through some nice points, -1, -1, and 1, 1. The reason this gets really big around 0 is if you plug in a small number, what's the reciprocal of a really small number? A really big number, okay? And if you plug in a really big number, its reciprocal is a really small number, okay? But you can't plug in 0, so we don't have any values here. And this will never equal 0 because the numerator is a 1. It will never equal 0 either, okay? The only way that we could get this to equal 0 is if the top was 0, and it's not. It's a 1. It doesn't even have a variable in it. Good there? Okay. Pretty simple rational function. Okay, this is the reciprocal square graph. Does anybody remember how these compare? Like, what does this one look like? It's always positive, okay? So the square makes sure that it's always positive, and when we square something, it's going to be a little bit steeper and a little bit flatter out here. So it's going to end up looking something like this. Like that. We've still got a vertical asymptote here at x equals 0. Remember, that vertical asymptote is there because we can't plug in a 0. And we've still got a horizontal asymptote of y equals 0, because it never actually comes down and touches the x-axis. And it goes through 1, 1 and -1, 1. Never crosses the x or the y-axis, but that's what it looks like. Okay, any questions? Okay, then keeping in mind what those graphs look like, those parent graphs that we've already got memorized, what would happen to the graphs if the functions changed to, so for this first one, 1 over x plus 1, what would we do to the graph? Yeah, if you know what the shape is, adding 1 after the fact just moves it up 1. Okay, what would this one do? Down 2. Okay, that's it. Okay, that's not bad, is it? So we actually could have called these rational functions last week when we were learning about those parent functions. Okay, those are some very simple rational functions. Polynomial on the top, it's just a number. Polynomial of degree 1 on the bottom here, it's a rational function. Okay, wherever it's 0, we have a vertical asymptote. Okay, and this one right here, polynomial on the top is degree 0, polynomial on the bottom is degree 2. And again, we've got that vertical asymptote there. So let's talk about these vocabulary words. These are going to be really useful. Okay? So let's talk about what a proper rational expression is. Proper rational expression is where the degree of the numerator is lower than the degree of the denominator. Okay? So just like in our example up here, this was proper. The top was smaller than the bottom. These two were improper. Okay? So if it's an improper rational expression, the degree of the numerator is equal to or greater than the degree of the denominator. So the top's a higher degree polynomial. So for this first example, all we want to do is this. Just look at it and say, is it proper or is it improper? That simple. So, proper or improper? This one's going to be proper. Proper because this is degree 1 and that's degree 2. Okay? Proper or improper? Okay, this is improper. And how about this one right here? We've got an x squared on the top and just an x to the first on the bottom. So this is going to be improper. Okay? All right. Now, if you know whether it's proper or improper, that can really help you figure out what the graph looks like. Okay? In fact, it can help you figure out where some of the asymptotes are. So if you're graphing a rational function, we use proper and improper to help us find the horizontal and oblique asymptotes. Now, oblique is a new vocabulary word for you. Oblique means slanted, okay? Kind of tilted a little bit. Okay, now this looks like a ton of stuff to remember, but it's pretty easy, okay? If the rational function is proper, then the horizontal asymptote is y equals 0. It's that simple. If you look at it and say that it's proper, then the horizontal asymptote, out near the ends, it's got to approach y equals 0. Okay? So on this one right here, what would the horizontal asymptote be on this one? It'd be y equals 0. Okay, now let's come up here and let me show you something that you already know how to do. Okay, look at this right here. Proper or improper? 1 over x. Proper. What's the degree of the top? 0. What's the degree of the bottom? 1. So it's proper. What's the horizontal asymptote? Y equals 0. Didn't we figure that out right here? Okay, let's take a look at this one right here. Proper or improper? Proper. So what's the horizontal asymptote? Y equals 0. And there it is right there. Okay? So if it's proper, it's really easy. You can just say, hey, the horizontal asymptote is y equals 0. Now here's the great part. Even if it's improper, it's really not that bad, okay? So there are 2 possible outcomes when we're dealing with rational functions that are improper, okay? They're what I call the good type and the bad type of improper, okay? The good type is just as easy as if it were proper. So if it's the good type of improper, this is the good type. The degree of the top is the same as the degree of the bottom. So let's take a look at these 2. They're both improper. Which one is the good type? B. This is the good type of improper. What's this one? This one's the bad type. Okay? Now, I'm not trying to make the rational expression feel bad or anything like that. I just don't like dealing with those when they're the bad type of improper. Okay? So here's the good part. If it's the good type of improper, then the horizontal asymptote is y equals the leading coefficient of the top over the leading coefficient of the bottom. Leading coefficient of the top over the leading coefficient of the bottom. Now, if it's the bad type of improper, then you have to do long division in order to figure it out. Okay? This usually produces an oblique. What does oblique mean again? Slanted. It usually produces a slanted asymptote. Okay? Okay, so I'm going to leave this right here so you can still see that. Find the horizontal or oblique asymptote for each of the following. Now, these are the examples up above, so these hopefully are pretty easy. Is this proper or improper? Okay, this one is proper. Okay, it is literally this simple. Once you figure out that it's proper, I'm going to write the word proper, and then I'm just going to write an arrow, and I'm going to write the horizontal asymptote is y equals 0. Done. End of story. We're finished with that one. Let's take a look at the next one. Proper or improper? Okay, this is going to be improper. Good or bad? Good. And then I'm going to write y equals, so it's going to be the leading coefficient of the top over the leading coefficient of the bottom. What is the leading coefficient on the top? 2. What's the leading coefficient on the bottom? Okay, coefficient, not degree, coefficient. It's a 1. So it's 2 over 1. So that means the horizontal asymptote is y equals 2. That's it. Okay, now, put your pencils down. Just think for a second. This looks absolutely awful, but we already know something about what this graph has to look like. Out near the ends, it's got to get close to this line right here. So it probably runs along here and goes up, or runs along here and goes down, runs along here and goes up. It could do some weird things in the middle, but we know out near the end, it's got to look like that horizontal asymptote of y equals 2. That is its end behavior. Okay? Any questions there? Okay, so proper is a piece of cake. If it's proper, we write y equals 0 as the horizontal asymptote. That's it. If it's improper and the good type, we just write y equals the leading coefficient of the top over the leading coefficient of the bottom. End of story. We've got our horizontal asymptote. Okay, is this the good or the bad type? Okay, so here's what we do. This is improper. It's the bad type. And the reason it's the bad type is we're actually going to have to do some division. So you remember how to do polynomial division from 1010? We're going to take x plus 2 and we're going to put it into x squared minus x, plus x minus 3. What do we multiply x by to make it an x squared? An x. So I'm going to multiply, I get an x squared. This is going to be a positive 2x. Then I'm going to subtract. So that's going to be a minus x and a minus 3. And what do I multiply x by to make it a negative x? Negative 1. So if I multiply here, this is going to be a negative x. That's going to be a negative 2. So that's going to be a plus. That's going to be a plus. And we've got a remainder of negative 1. So here's what I get. Everybody watching? Here's the quotient. Here's the remainder. This is the divisor. So the answer here is the quotient plus the remainder over the divisor. Now, here's the great part about figuring out what the oblique asymptote is. The oblique asymptote on this one is y equals x minus 1. That's our oblique asymptote. All it is y equals the quotient. See what I set up here? If that's the case, we use long division, and then y equals the quotient is the asymptote. So here's the quotient. We don't even have to worry about the remainder. Just figure out what the quotient is, and it's going to be y equals x minus 1. So it looks like this. Okay? Any questions there? So horizontal asymptote, if it's proper, y equals 0. If it's the good type of improper, it's y equals leading coefficient over leading coefficient. Okay? And if it's the bad type of improper, we just do a little bit of long division and write y equals whatever the quotient is. That's it. We don't have too many of these. We have a couple of them. Okay? They're actually not that bad. Other than the division, they're actually easier. Okay? All right. Any questions there? Everybody understand the words proper and improper? Okay? All right. All right, let's keep going then. Okay, after we find the horizontal and oblique asymptotes, we need to find the vertical asymptotes and something called a hole. Okay? It's possible for some of these graphs to just be running along, looking just fine, and then they'll just be missing a point. Okay, there's a hole in that graph. Okay, and the way we find those, the reason we have vertical asymptotes, like we mentioned before, is they're created when the denominator equals 0. Okay? So a lot like the ones that we graphed up here, the reason we had a vertical asymptote here was because that's where the denominator equaled 0. There was a domain issue there. Vertical asymptotes and holes are created by domain issues. Okay? So let's take a look. Here's what we do. Find the vertical asymptotes and or the holes for each of the following functions and state the domain. So the first thing we do is we factor each one of these. So I'm going to take this and I'm going to write this as x minus 1 on the top. There's no factoring to be done there. X minus 1 and x plus 1 here. Now we look at that And it's actually easier to figure out the domain first. Okay? What's the issue that comes from this one? What makes that denominator equal to 0? Or that factor? That's going to be a 1. And how about this one? Negative 1. Okay? So those are the two things that it can't equal. So the domain is everything except for plus and minus 1. Okay, and is everybody watching? Okay, I can simplify this just a little bit. What can I cancel? Okay, I can cancel the x minus 1 with an x minus 1. So that means what's left is a 1 on top and an x plus 1 here. Now, the one that cancels, this one right here that canceled, if it cancels, it's now a hole. There's going to be a hole in the graph right there. If it stays around, like what makes this equal to 0? Still negative 1. This is a vertical asymptote. Okay? It's that simple. Factor it. Identify the domain issues, what makes the denominator equal to 0. If it cancels off, if that problem cancels off, then it becomes a hole. If it sticks around, then it's a vertical asymptote. That simple. Any questions? Okay, you'll notice I'm using the same rational functions over and over again, because by the time we're done, we're going to know a ton about these three. Okay, so let's take a look at this guy right here. We'd want to factor this. Does the denominator factor? We need two numbers that multiply to be negative 8 combined to be positive 2. X plus 4 and x minus 2. Let's see, does the numerator factor? Could we get numbers that multiply to be negative 8 and combine to be positive 7? Multiply to be negative 8, combine to be 7. I think we can. So let's do this. I'm going to do a 2x here, whoops, and an x here. Let's see, if I put a 4 here and a 1 there, those would make an 8 and those would make a 1, so I could make a 7 out of those. I need a positive 7, so that's going to be a plus and that's going to be a minus. Now, if you're good at factoring and you can do guess and check really quickly, go ahead and do that. If you need to factor this using that method where we multiply the 2 with the negative 4, do the trinomial grouping, rewrite that middle term and that sort of thing, that's totally okay. Please, whatever you do, everybody listening, don't just say, I think I got it right. Because these are long problems, they're pretty complicated, and if you make a silly mistake like put the 4 in the wrong place and the 1 over here, and then start canceling things off, it's going to get really frustrating because you're going to get it wrong. Just take the time to double check. These multiply to be 2x squared. These multiply to be negative 4. These multiply to be positive 8x, and those multiply to be negative 1x. So that's a positive 7x. So did we factor it correctly? Okay. The next thing we do is we identify, are there any problems with the domain? Are there any numbers that we can't plug in? What can't we plug in here? Okay, negative 4 and a positive 2, right? Can I simplify this in any way? Yep. So x is not equal to 4 or 2. There's the domain. And I can cancel this off. So if that cancels, what does that mean about x equals negative 4? That's a hole. Since this stuff sticks around, what is this? Vertical asymptote. And the simplified version would look like this. 2x minus 1 over x minus 2. That's what it would look like when it's simplified. Okay, are there any questions? Okay, can I slide this over? Okay, let's take a look at this one. Let's see. It's already factored, right? That numerator, does it factor at all? Can you multiply to be negative 3 combined to be positive 1? Nope. So there's nothing that can be done to factor this. What's the number that you can't plug in? Negative 2. So if you can't plug in negative 2 and it doesn't cancel, what does that mean negative 2 is? Vertical asymptote. That's it. So you're going to be given some problems where all they ask you to do is say whether it's proper or improper. Then some will say, find the horizontal or the oblique asymptotes. That's a question about whether it's proper or improper. It's just one extra step. You've got to figure out if it's proper, y equals 0 is the horizontal asymptote. Good type of improper, leading coefficient over leading coefficient. If it's the bad type of improper, it's going to be y equals the quotient when you divide. Okay? When you're finding holes and vertical asymptotes, then it's just a question of, well, what can't you plug in, and does it cancel or not? We can't plug in a plus or a minus 1. This one cancels, so it's a hole. The other one's still a vertical asymptote. Okay, are there any questions? Yeah. No, no. Those would multiply to be 2 and combine to be positive 1. Yeah. They got to multiply to be negative 3 and combine to be positive 1. Okay, anything else? It's not too bad. That's a half hour. Okay, there you go. Okay, one more idea to cover, and then we can actually graph one. Whole thing. Find the x-intercepts. This is actually pretty easy. This looks ridiculously confusing. Okay, clear your mind for just a second, especially the people that were in my 10-10 class. How do you find intercepts? Somebody says, hey, I need you to find the intercepts. What do? You make a little xy table. You plug in a 0 for x. What will that find for you? That'll find the y-intercept. Plug in a 0 for y, and that will find the x-intercept. Okay? So if we're asked to find the x-intercepts, or the zeros, or the roots, or the solutions of this, we want to know when this equals 0. Now take a good look. When does that equal 0? Okay, what would be the only part of a fraction that could make it equal to 0? Only the numerator. Only the numerator can make it equal to 0. Now on this one, let's take a good look at this. Since we've been exploring these three functions for quite a while now, let's take a look at this right here and let's think about this. Here's what we did before, okay? Because finding x-intercepts should be one of the last things that you do, generally speaking. We did this. We wrote it as x minus 1 over x minus 1, x plus 1. We canceled that off, and we got 1 over x minus 1. So what you should use is the simplified version. This is the simplified version. Let's set that equal to 0. Now, the only way that this can equal 0 is if the top equals 0. The bottom could never be the thing that makes it equal to 0, because what if the bottom were 0? Then it doesn't work. It's undefined, right? So only the numerator can produce x-intercepts. So the cool part about finding these is you don't even have to worry about the denominator. We're going to use the simplified version, set it equal to 0. Does this ever equal 0? Okay, so we're going to write no x-intercepts on this one. Let's use the simplified version of this one. The simplified version is right here. 2x minus 1 over x minus 2. Let's set that equal to 0. Again, these look awful, but take a look. The only way this is going to equal 0 is if the numerator equals 0, so I don't even need to worry about the bottom. When does 2x minus 1 equal 0? When x is positive 1/2. Okay? That's going to be the x-intercept. Okay? And let's take a good look at this one right here. This was the simplified version. What's the only part of this that could make it equal to 0? Just the numerator. So when does x squared plus x minus 3 equal 0? Let's see, that's a quadratic. How do we normally solve a quadratic? Okay, we factor it if we can factor it. If you can't factor it, then we use the quadratic formula. So this is going to be negative 1 plus or minus 1 minus 4 times a times c. So that's going to be a 1 and a negative 3 all over 2. So this is going to be negative 1 plus or minus. Is that going to be 1 plus something or 1 minus something? 1 plus. So that's going to be a 13. So this actually has two x-intercepts. One of them is negative 1 plus radical 13 over 2, and the other one is negative 1 minus radical 13 over 2. Yes, Alex?
Couldn't you check the discriminant first to see if it's greater or less than 0?
Sure.
If it's less than 0, then it's...
Then it wouldn't have any x-intercepts. Yeah, you're right. But this one's positive, so there are some x-intercepts. Okay. Any questions? Okay. So those are the basics. That's it. Yeah. Actually, you have some easy problems in 4.3. They don't ask you to graph a whole bunch of stuff. They just ask you to identify features of the graph. So they're asking you things about, hey, tell me whether it's proper or improper. Figure out the horizontal asymptote. Figure out if there's a hole. Figure out whether there's a vertical asymptote and where they are. State the domain and the range and stuff like that. And on some of them, they give you a graph and then they just ask you to find answers about it. So, domain and range. So, if we're going to find the domain of this, now it doesn't even tell us what function it comes from. The domain are the x's. So remember, I've always said the easy way if you're given a graph is take the graph and squish it on the x-axis. So if we take all these points and squish them down here, all these points and squish them up, squish them down, squish them up, what part of the x-axis would be covered? Okay, the whole thing except for a couple places. Do I have any answers right here? No, because that's where a vertical asymptote is, right? What about right here? Not there either. So any x you want except for plus or minus 1. Okay, what about the range? If domain are the x's, range are the y's, so take the graph, squish it onto the y-axis. So if I took all of these points, squished them over here, all of these points, squished them over here, and all the points down here, squished them over there. Well, my gosh, take a look at this piece right here. It starts from way down here at negative infinity, and it's just one continuous piece from the top to the bottom. So what's the range? Negative infinity to infinity. It's all reals. Okay? Good? Okay, watch. Let me come back here. What's the range for this one? Everything, all reals, except 0, okay? It never actually touches 0, okay? Now, take a look at this branch and this branch. See the two pieces there? That's kind of like having this branch here and this branch here, okay? If it were just the two of those and we left out the middle, it wouldn't include 0, but look, this one comes up and it covers every single one of them. Everybody okay with that? Okay. All right. Intercepts. When it says intercepts, what are they talking about? X and Y intercepts, both of them. So you want to indicate all of them. Does it ever cross the x-axis? Right there. Does it ever cross the y-axis? Right there. The only place this crosses is 0, 0. Okay, that's it. It's the x and the y intercept. Okay. Horizontal. If it's horizontal, it's like this. Is that y equals a number or x equals a number? Y. Horizontal lines are y equals a number. Okay? Is there a horizontal asymptote here? Dotted line comes out here, approaches the y-axis, or excuse me, the x-axis, comes up here. It's y equals 0. Okay? Vertical asymptotes. Y equals negative 1. X equals negative 1 and x equals positive 1. Those are the two vertical asymptotes. So there's the horizontal asymptote and there's the vertical asymptote. Oblique asymptotes, if any. Are there any oblique asymptotes on that? Are there any slanted lines there? Nope. Okay, let me give you a hint. If there's a horizontal asymptote, there won't be an oblique asymptote. And if there's an oblique asymptote, there won't be a horizontal. It's either one or the other with these. Okay? All right. Any questions? Okay. Perfect. That's enough that you can do the assignment from 4.3. Don't put that away yet. Okay. See those steps 1 through 7? You don't have to go through those steps in that exact order and do this, then this, then this, then this. These are general guidelines. Okay? So this one says locate horizontal or slanted asymptotes, oblique asymptotes. Okay? And you do that by figuring out whether it's proper or improper. Factor the denominator, find domain issues. Now, does that sound familiar so far? Locate vertical asymptotes and holes. We've done a little bit of that already. Find the x and y intercepts. Draw the asymptotes and holes and all that sort of stuff, any points that you've got on the graph. Put all the information together to make the graph and then just label it. Okay? So this is not a step-by-step procedure, but they're pretty good guidelines, and they're basically going through and saying, well, how would you do each one of these? So does that look familiar? Okay. First thing we're going to do, horizontal or oblique asymptotes. And the way we answer that is proper or improper? Proper. If it's proper, what's the horizontal asymptote? Okay, so we got one thing taken care of. Okay, the next thing we do is we factor the denominator. Okay, and the numerator. We'll factor everything. What numbers can't we plug in? 1 and -1. Okay? This one cancels. So the simplified version is 1 over x plus 1. This one here canceled. What does that mean about this guy right here? It's a hole. What does that mean about this one? Vertical asymptote. So here's what I've got so far. I've got a horizontal asymptote. I've got a hole, I've got a vertical asymptote, and I've got this simplified version that I can work with now. Any questions? What step are we on? We're already on 4. That's not much work to get to step 4, is it? Okay, let's find intercepts. Does this ever equal 0? Nope, never equals 0. So we don't have an x-intercept. There's no x-intercept. Is there a y-intercept? Can you plug 1 in and get an answer? What do you get? 1 on top and 2 on the bottom, so we get 1/2. Okay, so between this piece, this piece, this piece, and that piece of information right there, we can start sketching this. Okay, now I'm going to do the final answer in blue, but I'm going to mark these down in black. Horizontal asymptote at y equals 0. So I'm just going to do this. Okay, horizontal asymptote there. Where's the vertical asymptote? -1. Okay, there's a vertical asymptote. So I've got y equals 0. That's a horizontal asymptote. X equals -1. That's a vertical asymptote. What is this right here? That's a hole. Everybody watching? I don't think we've graphed one with a hole before. So here's what you do. Draw a little dotted line and just write the word hole by it. All that's going to do is remind you, hey, when I start graphing this, once I cross that line, I know wherever my graph is, I need to make a little hole in it. Okay? What's this? The y-intercept. It's a point on the y-axis. So I'm going to come back here and I'm going to put a point at 0, 1/2. So that's what I've got so far. Any questions?
What does that say for the x point, the second x point?
This, what one? Here?
Yeah.
None. There's not an x-intercept. Never crosses the x-axis. Never touches it. Okay? All right, now, if this is a vertical asymptote, and it goes through right here, so the graph's got to go through right there somehow, and then it's got a choice. It's either got to go up along the vertical asymptote or down along the vertical asymptote. Can somebody tell me which it has to be? Why does it have to go up? Why can't it go down? Okay, Emily, say that louder.
There's
There's
no X-intercept.
no x-intercept, so it's got no choice. It has to go up. Okay, now over here, could it go down below here like this? Could it skirt down below there? Nope, because it doesn't have any x-intercepts, so it's got to do something like this. Now, what did I say we left that little dotted line there for? There's a little hole in the graph right there, and then it goes like that. Okay, now, there's going to be part of the graph over here, and it's either going to look like this, all on the top, or all on the bottom. Can somebody tell me why it has to be either all above or all below? Emily, say that louder again. There are no x-intercepts. So it's got to run along the horizontal asymptote, either above or below, and then go up if it's above, down if it's below. How could we find out which it is? I've got a number over here. I'm sure that 0, 1/2 is on the graph. Let's pick a number over here. Charles, pick a number. 42. Let's pick negative 42 since that's over there. If I plug in a negative 42 here, I have a 1 on the top, a negative 42 plus 1 on the bottom. What's the bottom? Negative 41. So it'd be negative 1/41. So is that above the x-axis or below? That's below. So the graph's got to go like this. Okay? And that's it. There's your first rational function. So here's what I want you to do. I want you to review your notes. Get going on 4.3. If you come tomorrow without doing 4.3, if you think today was tough, wait till we start plowing through graphing a bunch of these. Okay? So get started on that. 4.3 is pretty easy, I think. Yeah.
I understand how you get the y-intercept and plug in extra 0, but where do you plug in extra 0 to get 1/2?
Hang on one second.